Okay, so today we will talk about chemical safety and hazardous waste management. So first and foremost, why do we need to talk about chemical safety? So there are four reasons. The first is it creates a better working environment. When we are safe, we don't have to worry about bad things happening to us, and it allows us to be more productive. So second is you are students currently of a science course, and this will, in the future, allow you to be called trained staff. So you will be trained in the sciences. And trained staff is hard to replace, and nobody wants to be injured. So dealing with chemical safety allows us to prevent the loss of trained staff. The third is accidents also incur costs in replacing or repairing equipment, not to mention the different wasted reagents. So equipment is expensive, materials are expensive. And so if we conduct ourselves in a safe manner, then that would mean that we are also protecting the equipment and materials in our lab. And finally, it is required by law. The law in question is Republic Act 11058, or an act strengthening compliance with occupational safety and health hazards and providing penalties for violations thereof. So whether we like it or not, we should be talking about safety. So how do we recognize the hazards in an in a laboratory setting? So what is a hazardous substance? A hazardous substance is a material or substance that poses a physical or health hazard. So what is a health hazard? Health hazards occur when a chemical produces an acute or chronic health effect on exposed individuals. And meanwhile, a physical hazard is a when a chemical has a physical property of a substance that causes direct harm. So an example of the physical hazards are flammable, explosives, pyrophorics, corrosives, and reactive substances, while health hazards are your toxins, carcinogens, teratogens, and sensitizers. And we will talk about those in a little while. But first, let's recognize the routes of exposure for certain chemical hazards. So there are two kinds of hazards. There are their acute hazards, which cause immediate harm. So an example of an acute hazard is for example, hydrochloric acid. It will cause immediate harm because you will get chemical burns when you are exposed to hydrochloric acid. Another kind of hazard are the chronic hazards, which do not cause immediate harm, but causes harm over a long sustained period of time. An example of a chronic hazard would be something like lead. So lead is mostly harmless when dealt in small amounts and in small time scales, but over time, it becomes more and more dangerous because you develop lead poisoning. What do you think? How can anyone raise their thumbs up if they think that acute hazards are more dangerous? Can you raise a thumbs down if you think it's uh, chronic hazards are more dangerous? So what do you think is more dangerous? Let's see. Let's see your reactions. So Juliana says it's chronic hazards. How about the rest? Corinne, Gabrielle, they're all saying chronic hazards. And you would be correct. Yeah. So chronic hazards are essentially more dangerous because they deal damage over time, essentially. So there are four routes of exposure. You can have your hazards ingested, which is through the mouth, inhaled, which is through the lungs, injected, which is when it is administered via a hypodermic needle or maybe even through a cut in your skin. And even in some cases, if you just contact with your skin. causes a hazard. So we should be cognizant of the routes of exposure, and that is why we need to be uh, aware of safety protocols because that is what will be protecting us from the hazards. So we hear toxicity all the time. What do we mean when we say the word toxic? So toxicity refers to the degree to which a chemical can cause damage. According to the father of modern pharmacology, Paracelsus von Hohenheim, all things are poison and nothing is without poison. The dosage alone makes it so a thing is not a poison. Simply put, anything, anything is a poison. So even the most mundane of things is potentially hazardous. So examples of this over here are alcohol. Alcohol is 13 shots taken all at once will kill you. Coffee, 118 cups taken all at once will kill you. And water, 6 liters taken all at once will kill you. So I'm not giving you any ideas on what if you'd like to kill someone or yourself with any mundane chemical, but you know, it's nice to know that the most ubiquitous, the most seemingly harmless chemicals can actually do a lot of damage with the uh, right amount. So that is why all chemicals must be properly labeled. And the original label of the chemical is the best indicator of the hazards that chemical possesses. This also means that we should be always labeling the containers of our chemicals. Even not just in the lab, but even outside the lab, in our homes. Like we always hear stories about uh people, for example, storing bleach in containers of mineral water, and then someone accidentally drinks it, then a that is a hazard because they didn't manage to relabel the container. So things like that. So I'd like you to inculcate the value of always labeling your stuff because you never know when that will lead to an accident. So the here are the what do you call this? The pictograms, the safety pictograms in a GHS compliant label. So a GHS stands for Globally Harmonized System, and which is a system for dealing with hazardous chemicals. So you might need to familiarize yourself with these pictograms. So the exclamation mark is irritant. The gas tank is a compressed gas. The skull and bones denote toxic. The hand and metal bar being eaten away is corrosive. The silhouette of a person with something burning inside them is a health hazard. The dead fish and the dead tree are environmental hazards. The circle, which is on fire, will be the oxidizing agents. The fire is flammable, and the bomb going off is explosive. So, recognizing hazards. So, safety data sheets are so we are able to recognize hazards using what they're called safety data sheets or otherwise known as material safety data sheets. So these are documents that outline the hazards found in a chemical and what measures to undertake if that chemical comes into contact with a, sorry, with a person. So these documents must be within reach at all times in a laboratory. So you are actually required to look at the MSDS for each chemical you will be using before you enter the lab. So it's very easy. You can just Google any any MSDS. So I can show you that right now. So for example, let's search for HCl MSDS. And then just click on the first link, and then you'll get this. It's basically the SDS for HCl. You'll see the word danger, and then it causes skin, eyes, or burns, causes digestive and respiratory tract burns, etc., etc. So potential health effects, first aid measures, firefighting measures, accidental release measures, handling and storage. So everything you need to know about this chemical you can find in the SDS. So what are the types of hazards that I was talking about earlier? So these are the health hazards. So there are a number of them. So a carcinogen, it causes cancer, and a mutagen causes other unwanted mutations. So it can be either a somatic cell mutagen, which can target any cell in your body, or it can be a germ cell mutagen, which uh, affects your germ cells or your gametes, your sperm and your egg. No? So you also have teratogens, which induces birth defects. An example of a teratogen is thalidomide. Thalidomide, ironically, was marketed as a medicine for pregnant women on who are experiencing morning sickness. With if you're familiar with the concept of morning sickness, it's during the first trimester, women often get very nauseous when they are pregnant. So they took thalidomide, which was an anti-nausea medication, but turned out that it was actually a teratogen, and up to 10,000 children were born with birth defects when thalidomide was uh, available. So that's uh, that's a cautionary tale for everyone to be vigilant of the things they put in their bodies. Irritant, it causes irritation to epithelial tissue. So it's not just your skin, but also the epithelial tissue in your mucous membrane, in your respiratory tract, in your gastrointestinal tract. Those things can be irritated by irritants. Asphyxiants, these are the gases that deplete oxygen in the environment. An example of this would be carbon dioxide or liquid nitrogen. So what happens is when you release that into the environment, they compete for the space that oxygen would normally fill up. So they deplete the oxygen in the environment. And finally, we have sensitizers which cause allergy or allergy-like symptoms. So they actually invoke a immune response in you, which causes allergy-like symptoms. Are you all following so far?
Yes, sir.
Okay. So in order to minimize hazards, we use this hierarchy of controls. So we need to prioritize certain interventions over others. This is why we have this hierarchy of controls. And on the top is elimination, which is the most effective way of minimizing a hazard. You just get rid of the hazardous substance in the system. So substitution is replacing the hazard with a less dangerous alternative. So for example, instead of using benzene, which is a carcinogen, you can replace it with something like ethanol, which is just an irritant. Oops, sorry. Okay, so next under elimination substitution will be the engineering controls, which we will talk about later. And then administrative controls, which is the way we change the way people work to make them more safe. And then finally, we have PPEs, which protects the workers from the hazards directly. So you will notice that PPEs are actually the least effective way of dealing with hazards, and elimination is the most effective way. So here is an example of an engineering control. This is a fume hood. It is a local ventilation device that limits exposure to hazardous fumes, vapors, and dust. So here are the ways in which we allow us to use a fume hood effectively. So number one, do not lift the sash above the recommended level. So on the fume hood in the labs that you will be using, you will see that the sash only goes up to a certain level. So do not lift it up above that. So number two, make sure that the exhaust blows at an appropriate rate, which according to the US OSHA, or the Occupational Safety and Health Authority, that is 7 feet per second. Do not store chemicals inside, and you always have to keep it clean. So a lot of you are biology, molecular biology majors. And so you will be using one of these in molecular biology. It's called a biosafety cabinet. So it is an enclosed ventilated workspace that involves it involves a filter and laminar flow. Basically, this allows any air from inside to go out and any air from outside to come in. So it's basically isolating the inside from the rest of the world so you can safely handle pathogens. So uh, when using a biosafety cabinet, avoid any activity that can disrupt the airflow within the cabinet. So you have to limit your hand movements, and you have to refrain from using open flames. You also have to decontaminate the surfaces of the biosafety cabinet before and after use. And you have to make sure that the HEPA filter, the high efficiency particulate air filter, is in good shape. So those are examples of administrative controls. Engineering controls. How about administrative controls? Administrative controls refer to practices in the laboratory that make it safer to work in. So these include the availability of safety signages and emergency phone numbers in visible areas within the laboratory. So we have that in our laboratories. The designation of a chemical hygiene officer who implements updates and administers a chemical hygiene plan. So this chemical hygiene plan is the one that details the different steps that ensure the safety of our lab workers, including you and me. And then the adoption of safety standard operating procedures. So this is what we are doing in line with that chemical hygiene plan, is to educate the learners, the people who will be using the lab, how to use the lab effectively. So when storing chemicals, so this is not going to be an issue for you right now, but in the future where you will have to be in a laboratory environment, maybe for your thesis or maybe later in your career, make sure to be aware of these things. When storing chemicals, the you should not store them above eye level. So eye level is actually very subjective, no? Because everyone has different heights, everyone has different eye levels. So a good rule of thumb is anything above 5 feet, please do not store chemicals above 5 feet, because it's very dangerous to reach up and grab a chemical above your head, right? So liquids should be stored with secondary containment trays that have a capacity of at least 110% of the capacity of the liquid. So you can see here in the picture, there are secondary containment trays that can be found that will not allow a spill to occur if one of the bottles breaks, for example. and they have to be stored with chemical compatibility in mind. So chemicals of the type within each box, so this is a chemical compatibility guide, can be stored together, although this is a typo, the oxidizing acid should not be here. So it's just organic chemicals and organic acids can be stored together. Inorganic acids cannot be stored together along with oxidizing acids and inorganic chemicals, alkali and reducing agents. So chemicals of the same type within each box can be stored together. Chemicals of the type that are in different boxes cannot be stored together. It must be physically be separated by distance or a chemical proof barrier. So please ignore the oxidizing acids here. This is a typographical error. Okay. So how about flammable liquids? Flammable liquids exceeding 10 gallons must be stored in a flammable storage cabinet. Potentially explosive materials must be monitored closely for as long as they are in the lab and must be disposed of 24 months after procurement. For peroxide-forming chemicals such as ethers, THF, aldehydes, and acetals, they should be inspected every 3 months for the formation of uh, signs of peroxide formation. So usually that involves a white precipitate or a cloudy white mixture forming near the surface of these chemicals. So let's go to PPEs. Now, the standard for a very long time for gloves was latex. Latex because it's comfortable, it is durable, and provides better grip to its alternatives. However, it is susceptible to attack by solvents, and there is a significant risk of allergy. So actually, a lot of people, I think around 40% of the population, is actually allergic to latex, myself included. So that is one of the downsides to using latex. But the biggest upside of using latex is that it is cheap. So for a long time, latex was the cheapest way to protect your hands. But as technology marched on, nitrile became just as cheap as latex. And it offers these advantages. It reduces the risk of allergies. It has excellent chemical resistance, but it can be easily compromised. If you've worn nitrile gloves before, you might know what I'm talking about. The slightest hole, the slightest tear in nitrile gloves basically makes the glove fall apart. And for some people, this isn't actually a weakness, but it's more of a strength of nitrile because it allows you to determine if the glove is compromised. So of course you can't use a compromised glove, and nitrile will for sure let you know if it is compromised. If it starts breaking down in your hand, then you know that there is a leak or a tear in your glove. So I think Dr. Alba already mentioned that you will be wearing long sleeve lab gowns in the lab. Please do, because short sleeve lab gowns have no place in a chemical laboratory. Let me reiterate, there is no place for short sleeve lab gowns in a chemical laboratory. The sleeves are meant to protect your arms from chemicals. I have experienced this firsthand. I have multiple chemical burns in my arms because I was wearing short sleeve lab gowns because that was the one that was given to me by laboratory. So please wear long sleeve lab gowns. Short sleeve lab gowns may be used in a microbiological laboratory. This is because in a microbial lab, you might need to wash your hands very regularly. Either way, the studies show that short sleeve laboratory gowns are not less likely to gather germs than long sleeve gowns. So for the safety goggles, so there are three types. You have safety glasses, safety splash goggles, and face shields. So safety glasses should be used when there is a chance for objects hitting your eye. They are not suitable for chemical splashes. So that is what splash goggles are for. So splash goggles should be used when there is a risk of a chemical splash occurring. And should there be a high splash hazard or when chemicals involved are very dangerous, then that's the time we will be using face shields. Okay, so let's go to masks. Surgical masks may be used when dealing with biological agents up to biosafety level 2 or workflows that don't release ultrafine particulate matter. So ultrafine particulate matter is uh, less than 3 microns in size. Otherwise, we will be using N95 masks or respirators when dealing with ultrafine particulate matter, toxic fumes, or highly infectious biological agents. So when dealing with compressed gases, you should know that compressed gases will expand rapidly upon release, depleting the oxygen in the room and asphyxiating all life. So compressed gas cylinders can become dangerous projectiles if mishandled or dropped. So in response to that, uh, you should place all cylinders such that its valve is accessible at all times, and the valve should always be closed when the gas is not in use. Furthermore, you should secure gas cylinders with belts or chains and ideally using cylinder clamps. You should fasten cylinders ideally individually or at maximum in pairs. So we have these in our labs, your emergency showers and eye wash stations. They uh, allow harmful chemicals to be flushed out if it comes into contact with a person's skin or eyes. Emergency showers must ideally be placed in such a way that can be accessed from any point of the lab within 10 seconds. The path must not be obstructed, and the shower must be able to dispose at least 15 minutes worth of clean water at sufficient pressure at any time. So for chemical spills must be cleaned up immediately. And you may be able to do this with the chemical spill kit. We have a chemical spill kit in all our laboratories. And if you don't, in your own laboratory, you can make a makeshift one using equal parts sodium bicarbonate, activated charcoal, and bentonite. So when we also need to prepare for emergencies, one way of preparing for emergencies is through the use of fire extinguishers. So fire extinguishers must be present in all labs and must be inspected regularly. Similar to other compressed gases, these must be secured to a wall through a belt or chain within 50 feet of any workspace. So for laboratories, it is recommended that our fire extinguishers are class B or ideally a mixed ABC type. So class B fires are the ones made by flammable materials such as oils. When using a fire extinguisher, it is remember the fast method, pull, aim, spray, and sweep. You pull the pin, you aim the nozzle towards the base of the flame, you spray the nozzle, and then you sweep from left to right to cover and smother the flame. Now let's go to the second part of our discussion, hazardous waste management. So a lot of this is actually just technical administrative controls on how to work with hazardous waste, but I feel that you need to learn some of this as well. So like chemical safety, there is a hierarchy for hazardous waste management. The most preferable is to simply just avoid making hazardous waste. But if it can be helped, you have to reduce, you have to reuse, you have to recycle, recover, treat, and only then should you dispose. So disposal is the least preferable means of dealing with hazardous waste. So actually, yeah. So what is hazardous waste anyway? So according to RA 6969, or the Toxic Substances and Hazardous and Nuclear Waste Control Act of 1990, Hazardous waste refers to all substances that are without any safe commercial, industrial, agricultural, or economic usage, or byproducts, side products, process residues, pet reaction media, contaminated plant or equipment, or other substances from manufacturing operations, and as consumer discards of manufactured products. So this is a flow chart that will help you determine what is if a certain waste is considered hazardous waste through RA 6969 or the Department Order 29, which is the material exemptions. Here is a list that summarizes that. So hazardous waste include wastewater, sludge, discarded chemicals, processed residues, byproducts, and industrial garbage. Meanwhile, non-hazardous waste refers to domestic garbage, treated wastewater, building demolition material except asbestos, septic tank effluent, mining spoils, and industrial commercial solid waste that do not contain prescribed heavy metals or hazardous waste. So what are some examples of hazardous waste? So all cyanides are considered hazardous waste. Acids below or equal to pH 2.0 is hazardous waste, as well as all alkali with the pH greater than or equal to 12. So arsenic, cadmium, chromium, and lead above 5 ppm are considered hazardous. Selenium above 1 part per million, barium above 100 part per million. Meanwhile, tin, beryllium, copper, zinc, tellurium, and thallium, all inorganic fluorides except calcium fluoride, at any concentration is considered hazardous waste, according to the DENR, as well as all oxidants, reductants, explosive or highly unstable chemicals, and highly reactive chemicals. So this is more of the technical side. I'll just breeze through this. So if you expect to generate hazardous waste, the facility should designate at least one employee to be the pollution control officer. We have that in PLSU. And they have to set up a storage facility that is accessible in case of emergency, enclosed but sufficiently ventilated, impervious to liquids and chemical resistant, and properly secured and not easily accessed by unauthorized personnel. I believe we have one of those at the SPRC. So if you have time, you can go check it out in person. Hazardous waste must be segregated by hazard classification and by chemical compatibility. Same to when we talked about storing chemicals earlier. And finally, all hazardous waste containers must be adequately labeled. So when we dispose of non-hazardous chemical waste, remember, not all chemicals are hazardous waste. So soluble salts, except those of heavy metals in sufficiently low concentrations, can be disposed down the drain. Now, some compounds, such as azides, need to be flushed with a continuous stream of water after disposal to prevent explosive fumes from forming. Because sodium azide, when in the presence of an acid, becomes an explosive chemical. Weak acids and alkali from pH 5 to 8 can be disposed through the sewers, and they can also be neutralized prior to disposal. Actually, it is more desirable that you neutralize your acids and alkali before final disposal. So we have to make sure that our waste containers are unreactive and the chemicals with the chemicals they contain. And you should always store the waste with chemical compatibility in mind. We should not store waste for more than 270 days, depending on how far away transport site is, or in amounts exceeding 1,000 kilograms per storage site. Meanwhile, there should be a facility where we store the hazardous waste. So it should have a floor constructed of material which will not react or absorb any waste, and which has no drains that provide a direct connection to the sewer. A continuous impervious curb placed in the perimeter of the floor in such a manner that waste will not escape between the floor and the curb, and then appropriate sidewalls and roof to protect the container from the weather. So here are some examples of hazardous waste Containment units, you have your safety and salvage drums. You have containers for used batteries and used fluorescent tubes. Also, you have small hazardous waste containers and hazardous waste transport boxes. So these are made out of high density polyethylene, which is very inert from chemicals. So here is an example of a storage site. It should contain a spill containment unit for hazardous waste, and all your chemicals need to be properly labeled. Cannot stress that enough. So here is an example of a hazardous waste label. It contains the contents and the waste class and waste number. So that is actually a, if you're interested, you can go read up on RA 6969 for more details on the waste classifications. So a lot of you will be taking up molecular biology in the future, or microbiology. So you should know that biological waste should be sterilized prior to disposal. So liquid waste, except those containing bleach, should be autoclaved and may be disposed directly into the sewer line. Does anyone know why we shouldn't autoclave bleach? Anyone? Okay, so actually, if you autoclave bleach, it will explode. So that is something that you have to be very careful of. Solid culture media should be autoclaved, resolidified, and then disposed. Oh, by the way, when I say that liquid waste from biological labs must be disposed, may be disposed directly down into the sewer line, there's a caveat there. It's directly towards the sewer line, not down the drain. Because in a traditional drain, there is a P-trap or a U-bend. The pipe goes like this because it prevents odors from escaping. But the problem with that is uh, liquid waste such as culture media might get stuck in that P-trap, and they might start breeding superbugs. So this has happened in a number of hospitals overseas already. So part of the reason why we have multi-drug resistant bacteria is because of people throwing culture media down the drain. So down the sewer, not down the drain. Very important. Sharks should be stored in a rigid container and disposed of as a biohazard. Meanwhile, animal carcasses or amputated body parts should be buried or incinerated. So what must you do if you plan to store, treat, or dispose of hazardous waste? So you need to secure the following documents from the EMP of the DENR, either an environment compliance certificate if you are going to be a big operation, or if you're a small operation, you're just like a small enterprise, then you can get away with a certificate of non-coverage, stating that I am not covered by the Republic Act 6969. And you should also have a hazardous waste generator ID. So a note, only DENR accredited transporters are allowed to transport hazardous waste outside generator premises. Likewise, only DENR accredited treaters are allowed to treat hazardous waste. So, in summary, chemical safety consists of mitigating the effects of hazardous chemicals either by removing them altogether or adopting practices that minimize the risk of harm from the chemicals. Meanwhile, hazardous waste management involves storing hazardous waste in the same way you can safely store your chemical inventory. And depending on the hazard level, chemicals may be disposed in the same way as other waste. Finally, in order to dispose hazardous waste, you must first secure a CNC, an ECC or a CNC, and a haz waste generator ID. And that would be all. Thank you. I am now open to any questions that may arise from the class. Anyone? I don't think any of you have any questions. So I think that would be it for now.